everyone, welcome to Data Nutshell. In the previous videos, we have seen RAID 3, which used byte level stripping with a dedicated parity disk. Now let's move ahead to RAID 4. RAID 4 keeps the idea of dedicated parity disk, but instead of stripping data at byte level, it strips the data at block level. This small change makes a huge difference in how the system performs. In this video, we'll cover how RAID 4 stores data, the role of the parity disk, performance struggles and weaknesses of RAID 4, and why RAID 4 was important but still replaced later. So let's see how RAID 4 works. Imagine we have three data disks, disks 1, disk 2, disk 3, and one parity disk. Unlike RAID 3, which broke data into bytes, RAID 4 breaks data into blocks, and each block is written to a single disk. For example, disk 1 will have block A, disk 2 will have block B, disk 3 will have block C. Then, when block D comes, it will go to disk 1 again. And for these blocks A, B, C, there will be a parity calculated A XOR B XOR C, which will be stored on the parity disk. So RAID 4 is block level stripping with dedicated parity disk. Just like RAID 3, RAID 4 uses XOR based parity for every set of data blocks across disks. The system calculates one parity block. So, for data blocks A, B, C, a parity block P is calculated with A XOR B XOR C, and that is stored on the dedicated parity disk. If any one disk fails and we lose any one of these blocks, it can be reconstructed using the remaining blocks and the parity block. Say if we lose B, B can be recalculated as P XOR A XOR C. So this gives RAID 4 the same fault tolerance as RAID 3, that is, it can survive failure of one disk. Let's see the performance characterization of RAID 4. The strengths are that it is great for random reads. Why? Because since the data is stored in blocks, you can read just one block from one disk without involving all disks. This is a big improvement over RAID 3, where every read involved all drives. It has high throughput for sequential reads because multiple disks still work together to deliver fast reads of larger files. The weakness is that parity disk bottleneck for writes because every write, no matter which data disk is targeted, also requires updating the parity disk. For example, to update block A, the system must also recalculate and update the parity block corresponding to that. So this means the parity disk gets a lot of write traffic and can become a performance bottleneck. So RAID 4 improves read flexibility compared to RAID 3, but it still struggles with the write performance. So RAID 4 was a big step forward, but it wasn't the final one because the parity disk bottleneck limited its scalability. That is why RAID 5 was introduced. In RAID 5, instead of having a single dedicated parity disk, the parity is distributed across all disks. So this eliminates the single heavy load parity disk and improves performance and reliability. So RAID 4 mostly served as a bridge between RAID 3 and RAID 5. So to summarize, we can say RAID 4 is block level stripping with one dedicated parity disk. It's better than RAID 3 for random reads, but it is still limited by the parity disk bottleneck in case of writing. And it is rarely used today because now we have better options like RAID 5, RAID 6, and so on. So in the next video, we'll cover RAID 5, the design that solved the limitations of RAID 3. So stay connected, subscribe, and hit the like button.